Hello everyone. The recent Kaggle competition WSDM Cup Multilingual Chatbot arena has ended, and the gold medal solutions have been published on the Kaggle website. Therefore, I have summarized the techniques used in those solutions. I feel that if we analyze each solution individually, we'll find they are written quite messily, and it's hard to remember useful information by looking at them separately. So I believe categorizing and summarizing the techniques from those solutions will be more helpful for our learning, and we can apply them to other large language model competitions in the future. As of making this video, gold medal solutions from 2nd place to 7th place have been made public. Thus, I have summarized these 6 solutions. First, the task of this competition is to give you a user's question and 2 answers, and then ask you to determine which response is preferred by the human. The difference between this competition and the previous arena competition is that it's more focused on multilingual, with questions and answering highlighting language diversity, while the previous competition focused more on English question answering. All these gold medal solutions use large language models to complete this task. However, the processing methods for large language models are divided into 2 types: sequence classification and causal language modeling. Specifically, for sequence classification, you would combine the user's prompt, response A and response B into one text, then tokenize it into a sequence, and train the model to classify, such as 0 representing response B is better and 1 representing A is better. And you can define it differently by yourself. And causal language modeling, on the other hand, is more likely the conversational mode of large language models, where you tell the model what role it plays and show it the prompt and 2 responses. Next, you ask it to judge which one is better, making the model generate just 1 letter to indicate which answer is better. And this is just an example. So different people can use different expressions for the formatting of the prompt. Then the model predicts the probability of the next token, mainly looking at whether A or B has a higher probability. Let's see the 2nd and 7th place used in the first method. Well, the 3rd and 4th, 5th, 6th, and 7th place all used the 2nd method. So I personally think the 2nd method is better because in the first method, sequence classification, the model initially doesn't know what 0 and 1 represent. So you need to train the classifier from scratch to let the model understand the meaning of 0 and 1. But in the 2nd method, you describe the task in natural language, and even without training the model, which was already trained on causal language modeling, can understand what you want to do, and it only needs to learn the standard people use to judge which answer is better. Therefore, this is a more natural training approach. For the model, there is also less to learn and making it simpler. The reason the 7th place used both methods is that they combined multiple models. They used models including JAMA, and since JAMA only has a causal language modeling head, they used the 2nd method for this model. For other models, they used the sequence classification. Next, let's talk about model selection. Different people use different models, with parameter sizes varying from 8B, 9B to 14B, 24B, 32B. We can see that Quen 2.514B was the most popular choice, indicating its strong performance in multilingual capacities. Next, a common technique in these gold medal solutions is distillation. So distillation means first training a larger model like 70B or 72B to complete the task. Larger models usually perform better than smaller ones. Then you use the logits from the larger models, that is, its predicted probabilities for each category or A, B, to train a smaller model such as 14B, 7B, 8B, or 9B. This way, the smaller model can achieve better results. But the third place solution found that a large model isn't necessarily needed. So they found that self-distillation with a 14B model was sufficient, which is sort of counterintuitive. Because normally we think the teacher model should be stronger than the student model. If the same model is used as both the teacher and the student surpasses the teacher, especially when they are the same size, it's sort of strange. And their explanation is that this might be label cleaning brought by soft logics. This means there's some noise in the original labeled data, such as when some people's preferences differ from the majority, which can be viewed as noise. And during training, the model might not fit those noisy data well, so its logics are less misleading than the actual labels. This is a kind of label cleaning, filtering out the bad parts through distillation. And we can understand it this way. Next, an important point is data augmentation for the winning. If you only use the original data provided by the computation, you won't win. There's actually a lot of data in the format of question plus 2 answers plus judgment on which one is better. So all solutions use additional data, but the completeness of those data varies. So the most complete data has question and 2 answers, and the annotation of which one is better. Less complete data has the question and 2 answers, but doesn't have which one is better. Even there is a least complete data, so they only have the question, even without the 2 answers. But that's okay, as you can use different models to generate the answers, and then use an already trained model to annotate, and only keeping data with high confidence annotations, and use those data to further train the model. This is actually also quite counterintuitive, because for data you are confident about, the model already knows which one is better. So why would using this data for the training still improve performance? So it's like, would a middle school student practicing addition and subtraction within 10 improve their math scores in middle school? Additionally, this method of generating data, annotating it, and then training models is very computationally intensive. So winning prizes in this competition requires significant investment in computation resources. There is also a concept called post-pre-training. So those models are already pre-trained, and then they adapted to this task through fine-tuning. But before fine-tuning, they added a post-pre-training step. So specifically, it's closer to fine-tuning rather than traditional pre-training. One difference from fine-tuning is the dataset. Post-pre-training uses data that doesn't completely match the task. So they could still be a question and 2 responses, and knowing which one is better, but this data could be primarily in English, with a different language distribution than the computation dataset. The benefit is that you can let the model know in advance what your task is to compare, A and B. Additionally, post-pre-training and fine-tuning can have different training objectives. For example, in the post-pre-training phase, your objective function might be to train the model to generate A or B as the next word, rather than other words in the vocabulary. While in the fine-tuning phase, you then use an objective function to make the model distinguish between A and B. And another difference in the first place solution between those 2 phases is that they use data augmentation in the post-pre-training phase, swapping positions of response A and B, thus doubling the data volume. But in the fine-tuning phase, they didn't do this. Additionally, in the post-pre-training phase, they only used a token length of 1024, while in the fine-tuning phase, they used 2048 tokens. And this can save training cost. Finally, let's discuss other commonly used tricks. First, when using any technique, you must consider hardware and time limitation. So the competition platform provides specific GPUs and time limitation, and you must adjust your strategy based on those limitations. Because without limitations, anyone could use a 72B model, but that would exceed the time limit. And they use some methods to address this. For example, some answers are quite long. And the second and first place solution mentioned that for long answers, they truncate a portion, and where to truncate, they found that cutting off the beginning or end would significantly decrease model performance, while cutting the middle parts works better. And other solutions might also use similar methods, but they didn't explicitly mention it. And another technique is to use different seeds during training. That means training the same model with different seeds, and it can yield very unstable results. So they average the model parameters of those models trained with different seeds. Therefore, they can get a model produce better results than the models trained with a specific seed. There is also a method for training data augmentation, swapping the position of the two answers in each sample, and the training data volume is doubled. So there is also another thing called test time augmentation, which means they first make a prediction, and then swap the position of A and B and make a prediction again, then average the two results. So this can eliminate model bias. For example, the model may tend to favor A when A and B are similar in their score, but swapping positions and averaging the logits or probabilities, you can eliminate this bias. And there is also model quantization. Different quantization methods have varying degrees of precision loss. And the third place method believe that auto-run method is best. And they also provide optimal learning rate for different model sizes. Finally, how to get the final results. So different solutions have different approaches. For example, the second place submitted two solutions. The first one uses Gemma to predict the question, and the responses are A and B. Then they use Llama to predict after swapping A and B. Then merge the weight ratio with the ratio of 3.3 to 1. And the second submission uses Gemma to predict all the samples. Then they use Llama to predict only samples where Gemma is uncertain. And then they summarize the results of those the samples Gemma was not certain with a weight ratio of 2.5 to 1. And the third place solution first used Quen to predict samples, sorted test samples by length, and for the top 25%, they did classification twice with A and B swapped. Then they averaged. Why only the top 25%? This is also because of the time constraints. They couldn't process more samples, and the remaining samples were predicted using FIFO. And the first place only trained one model for prediction. Then for samples with the smallest difference between A and B probabilities, they used TTA, swapping positions, predicting gain, and averaging. This also considers time, focusing resources on uncertain samples. The fifth place used a single prediction, but for uncertain samples, they looked at the number of numbers used in the responses. So the answer, or let's say response with more numbers, were considered more structured or organized, which user may prefer. So they pick that one as the better answer. And the sixth place first used Quen 2.514 for classification, and for uncertain samples, they used Gemma 2 to judge. The seventh place solution first used Gemma 2 9b to judge, and then for moderately uncertain samples, they averaged the probability of Gemma 2 and Quen 2.514b. And for the most uncertain ones, they used Quen 32b or Mistral 24b to judge, with a weight of 1.5, which is more than the Gemma's predictions. And this also considers time, because otherwise they would all use larger models to make the predictions. And this page lists some tricks that were found ineffective or they didn't work well. So I feel that many of those ineffective methods were discovered mainly for these tasks and don't have generality, so I wouldn't discuss them in depth. The following two might have more generality. The sixth place solution found that TTA wasn't useful, which is different from what other teams discovered. Additionally, they found that merging LoRa weights into the base model produced worse results, meaning that compared to first loading the original model and then loading LoRa, it would lose more precision. Finally, regarding hardware, two solutions mentioned the hardware they used. The first place used 40 A100s, and the fifth place used 6 A100s. So winning a gold medal requires substantial hardware support, which translates to significant cost. I might have overlooked some things, and I also welcome comments and suggestions on my video. If you are interested in summaries of Kaggle gold medal solutions, I can also summarize other recently concluded competitions. Thank you, everyone.